Okay, so tonight we have a relatively quick lecture, although I'll go fairly fast. The material is extremely dense. The discussion of a momentum balance and how you would use that momentum balance to then derive the Hagen-Poiseuille equation. I'm sure chemical engineer, where'd you go? Chemical engineer. Anybody else chemical engineer tonight? Nope. Okay. I'm sure that we're skipping over a few steps. Okay. Like when I took transport phenomena, we had to derive the shell balance. Then the best thing about deriving something is when you start knocking things out of it, you generally have some idea of what they do. So we're going to derive the Hagen-Poiseuille law. Now, for those of you who are not petroleum engineers or who may have some other issue with petroleum engineering, let me explain. We are not suggesting that you can use the Hagen-Poiseuille law to represent Darcy's law. We're suggesting that there's an equivalent capillary an equivalent tube that you can use to represent permeability. But what I wanted to do with this lecture is demonstrate the derivation of the Hagen-Poiseuille law, because we're going to apply the same concept as Hagen-Poiseuille law for Darcy's law. I've used that term like 6 times now. What is Hagen-Poiseuille law? Hagen-Poiseuille law is the law for laminar flow in a conduit, in a pipe. Okay? So if we take a whole bunch of little pipes and we assume we have Hagen-Poiseuille law valid in those and we bundle them up, then we can derive something like this. That's sort of the thought process. Now, sort of like in China, where they say that a bald man doesn't need a comb. Unfortunately, I explain how to use this, and then I talk about the derivation. I should have done it backwards, but that's okay. And then we talk about the units of a Darcy. The units of a Darcy. The Darcy unit that we use in petroleum engineering is contrived. It's a forced unit. What are the dimensions of permeability? It's length squared. It should be meters squared, right? How many of us have had Dr. Valco's class? Okay. Meters squared. What size is the number? 10 to the minus 14th, 10 to the minus 15th, 10 to the minus 16th. Well, if we start getting lower, I was thinking, but you're right, 10 to the minus 12. Do you want to carry around a briefcase full of zeros? No. So we use millidarcy and Darcy. Unfortunately, they defined it as a Darcy, and then we reverse it to a millidarcy because most places it isn't that. So the standard unit in petroleum engineering really is the millidarcy, but for the sake of argument tonight, it's the Darcy. And we'll derive the units of a Darcy. We'll also talk a little bit about what a Darcy means in the concept of an equivalent tube. And then last but not least, we'll talk about how to derive field unit forms. The last thing most people in this room, and I can guarantee you ladies, the last thing you want to think about is units conversion. But engineers have to do this. And I know you're thinking, I've got the units of monkeys over here and the units of ball bearings over here. Why do I care? Just use the metric system and everybody's happy. Unfortunately, the world doesn't work that way, because even within the metric system, we have other variations. It's ordinarily thinking it's kilogram, meter, second units. But what is it for the metric system for this? Well, it depends, because some countries or some regions are going to use different lengths or different, and maybe they don't use kilograms, maybe they use grams. There's also the centimeter gram second unit system, and that's actually what was used to derive the Darcy. So we'll talk about all that. If you're not confused now, you sure as hell will be. But this derivation or this lecture is really about understanding the characteristics of Hagen-Poiseuille flow and then taking those characteristics and doing something with them. And the first thing we'll say is, okay, the derivation of Poiseuille's law really requires some understanding of the forces on the system. We'll talk about that. That ends up being a momentum balance. And then we derive the average velocity. Now, we can't really measure the average velocity, but what can we measure? we can measure volumetric flow rate. Okay, so in petroleum engineering, we don't really worry about things we can't measure. Almost everything we do is in volume or volume per unit time and pressure, because those are things we can measure. Okay, so we're not going to talk. Where I'm going with this is that average velocity is volumetric average. Okay, what are the assumptions? The velocity at the wall is 0. That means there's a thin film, and so there's no slip at the wall. Not like my hand is sliding, but there's a film of fluid underneath there. Isothermal flow conditions, steady state, which is you can modify it for non-steady state, but we'll talk about that later. Incompressible, you can also modify it for compressible fluids. Single phase, we can modify it for multi-phase. Horizontal linear flow means no gravity effects. And then obviously the properties of the tube remain constant, the diameter, the roughness, etc. So what I've asked people to do in the past was to derive Puiseuille's law and develop Darcy's law from that, and then do a conversion from Darcy units, to centimeter square, and then derive Darcy units in Darcy's law in field units. These papers are the ones I've discussed before. I think I actually have you read a couple of these. Hubbard's equation is in the corresponding original notes lecture for this, which is in a separate folder, of course. This is the one where he tries to derive Darcy's law from Navier-Stokes theory, and he ends up having to make an assumption of permeability being, like I said, a direct geometric function of porosity. I mentioned that the other night. So the physical model is something like looks like this. This is a piece of rock. The conceptual model could be a bunch of holes in a block where we use Puiseuille's law for each one of those. And then the nice thing is you need to take classes sort of outside your sphere of comfort. And this was from my course. I took a hydrodynamics course in geology, and I learned two things in that course. Number one is they weren't nearly as complicated as petroleum engineering on the equations and the assumptions and so forth that they use in hydrology. And number two, geologists really don't like complicated things. So, but for having said that, they drew this complicated flow field, and then they show the average linear vector, or the average linear path, I should say, going through that. So this system has a net for all of these different flows. It has a net that looks like this. And I know you're thinking, well, how can you do that? How can you represent a complex system with something like that? Well, we do it every day. This would be impossible. Our two chemical engineers, how would you create a network and model it that way? Can you think of some way to do that? Can you create a network and model all of these different flow vectors? Sure. I'm not sure how you do it, but you could. And then what we say is that Darcy's law is the equivalent average path of that, I guess you'd say. Okay, so we'll start with Puiseuille's law, which I'm going to give you. We're going to derive this in a minute, but this is Puiseuille's law. And the first thing you notice is we take the flow rate divided by the cross-sectional area, diameter squared over 32, 1 over the viscosity, pressure drop divided by length, which is gradient. We're going ahead and multiply through by the cross-sectional area, pi r squared, and then we have 2 pi r squared, which is the diameter, of course, and then we have 32, which is just hanging around. So we get a 4 from this, 32 from that, and then we have r squared multiplied by r squared. We have a pi. So things get a little weird. We have a viscosity. We have a gradient. So we end up with pi over 8 r to the 4th. So for a single tube, this is not Darcy's law yet. This is a single tube, Puiseuille's law. We can represent it by this equation. And of course, everybody's saying, well, okay, the very first thing you notice is the radii is raised to the 4th power. Yep, that's right. Because it's a combination of the diameter term, and the cross-sectional area. Okay, so now what we're going to do is we're going to say, okay, we're going to add all these up. So we'll have a summation, and the total flow will be this. Obviously, the pressure drop across each system is the same. It has to be for it to be in equilibrium. So we can factor out the viscosity and the pressure gradient, and we're left with this. So in theory, this would be an equation that represents flow through porous media. You would have some volumetric average flow rate, you'd have a viscosity term, a gradient term, and then you have this really ugly constant. And that constant is pi over 8 multiplied by the summation from I equals 1 to n of the radii raised to the 4th power. And you're looking at this and thinking, well, this is pretty simple. I like this. Unfortunately, we have to admit that this is an oversimplification. The tubes usually are not straight. They also vary their diameter along the tube. There's all sorts of other things. But conceptually, for those of you who've never had a class in petroleum engineering, conceptually, this would be an analog for flow in porous media. Now, for those of you who have had a class in porous media, are you okay with this? You know, this looks, smells, and tastes like Darcy's Law. But what assumptions go into C? C is a constant made up of the dimensions of all those radii. Any comment anywhere, Mr. Sarkar? Any thoughts? No? Juan, you okay with this? Cam? We can just go home now? If you believe Pazouillet's law and you believe the order of operations that we took to get here, we're done. This is our analog with Darcy's law. We just take bundles of tubes, calculate a coefficient for the bundle. By the way, can we measure R sub I in situ? Of course not. Now, what do petrophysicists do, Mr. Aldana? Use a capillary pressure profile and reverse calculate the radius distribution. Highly idealized, but conceptually consistent. Okay? But you can't go the opposite direction. You do not know the distribution of radii. I'm not suggesting this was a waste of time. I'm suggesting that conceptually, I want you tonight to say, okay, I believe the laminar flow in pipes derivation, which we're about to perform. I believe that we can add these little pipes together and come up with an equivalent relationship. After that, we're leaving this. We're not going to come back. We're not going to talk about this again. We're going to assume that Darcy's law is correct and proceed on. Okay? So what can you tell your mom tonight? That whether it's flow in pipes or flow in porous media, there's a constant of proportionality between the pressure gradient, delta P over L, and the flow rate, QT, or velocity, however you want to express it. What's your mom going to say? That's great. If it's a boy, they're going to say, I'm really glad you learned something. If it's a girl, they're going to say, you got to work harder than the boys, right? So that's terrible. I shouldn't say that. I'm thinking about my daughter again. All right, so everybody's okay with this so far? No problems? All right. So now we have to derive Pazouillet's law. Let's see. Mr. Ravi Kumar, Mr. Bake, you had transport phenomena in undergraduate? Did you like it? No? No hobby English? Oh, we got a maybe here. What kind of school did you go to? Did you have to work hard, or did you just pay your money and they give you a degree?
The latter. I chose to go there. I just choose to be honest.
Did you go to Seoul National? Yeah. Okay. They made you work hard. You did not like transport phenomena. Yeah. We had a president named Carter, and one time they had an interview with him, and they asked him about his teacher at the Naval Academy. And they said, did you hate your instructor? He goes, it's a simple question. Yes, I hated him. And then they brought out the guy who was his instructor. And they say, how do you feel about, President Carter hating you? And he said, well, If he hadn't hated me, he wouldn't be president. So there you go. This guy was a tough one. Okay, so you hated transport phenomena. Sorry? Yeah, that's the key. How many chapters of the book did you cover? All of them, because it's a Chem E class. Yeah, we covered 18 chapters. There's 16 weeks in a semester. There towards the end, we were covering a chapter a day. And, you know, the nice thing about being a graduate student is that you almost believe you can fly, that you can levitate, you know. But when we were doing one chapter a day, I was not happy. That was really tough. And of course, the instructor, you know, he did like one chapter 3 weeks, one chapter 2 weeks, one chapter 1 week, and then went off on this tangent where we were doing this. But the derivation of the Hagen-Poiseuille law is a very classic one. We'll talk about it now. This is shear stress. This is shear rate. And the relationship between shear rate and shear stress. And by the way, I'm not an idiot. I just have like dyslexia. So actually, maybe I am an idiot, but I'm always going to get these two confused because I don't think in these terms. So tau is shear stress and dV dy is shear rate. And what's the proportionality between shear rate and shear stress? What's its name? Viscosity. Okay, so this is Newton's law for viscosity. Man, Newton was a busy guy. You know, he did a lot of stuff. Okay, so the way they like to describe it is take the top plate is static, and then the bottom plate moves. So they start, and there's a transient effect where the bottom plate moves and there's no velocity distribution. But eventually, there's a velocity distribution. Well, there's an instantaneous change, and then there's a velocity distribution that's a function of time. But eventually, at steady state, the velocity distribution is, because this is a linear system like this, it's a straight line. So this is trying to explain the top is static and the bottom is moving, and this is a velocity distribution. Where's the velocity distribution maximum? Well, in the middle, obviously, or sorry, at the contact point. And we'll talk about this some more in a minute. So now we go to an annular system, and we have to define terms. So I've marked A, B, C, D, E, F, and G. So A and B are the momentum flux across this. C and D are the momentum flux down the annular surface. And then E is the gravity force, which you can't ignore. And F and G is a pressure change. So this is actually a pressure change on the system. So we're going ahead and write the equation. Here's A, here's B, here's C, here's D, here's the gravity force, here's the pressure force, and of course all of these are, this is pressure times area, this is the gravity term multiplied by this particular set of, this is the circumference, and then the delta R, and then the length over which, and then these are the momentum fluxes in the annular space, and then these are the momentum fluxes across the cylinder. So we add them all up, and we have the first two, we have the second two, we have the gravity term, and then we have the pressure term. And of course, it's in equilibrium, so they're all set to zero. Anything wrong so far, my chemical engineering friends? You're okay? Very good. All right, so we just going ahead and say that C and D are the same. We're not going to worry about that. We divide through the whole system by 2 pi delta R, which gives us delta R, and then the differences in the shear stress, and then the difference in pressure, and again the difference in the height, or in this case the pressure head due to elevation. I guess you call it the gravity term, and then an R. And of course, it's still all equal to zero. So we separate, move things around a little bit. We multiply through by the delta R. We move this on the other side. And then we have an expression that looks like this. So now we take the limit as delta R approaches zero, which we know what happens here. That gives us a derivative. So now we're looking at the derivative with respect to the shear stress. And we have, again, sort of a pseudo pressure gradient here, and then again the gravity term. So we keep manipulating this, and then finally we're left with this form, which is our final form. And for horizontal flow, we don't have a gravity term. Now this is interesting, but it doesn't really help us. What do we need to do next, class? We need to integrate this. Okay, so the first thing we're going to do is we're going to determine the shear stress distribution, which is tau. And by doing that, we'll use indefinite integration. We'll just say that this is equal to y, and then we'll integrate the function indefinite integration. We'll factor out the pressure gradient. We'll leave only the r term. We'll integrate over r, which gives us, of course, this just integrates out, and we have r times tau rz, and then we have our pressure gradient term. We have r squared over 2 because this was r, and then we have a constant of integration. So what happens is the system has to be bounded. So whenever we're looking at solving this expression for radius at 0, this would be infinity. Sorry about that. This term would be infinity, which is invalid. So this term has to be 0. Okay. You chemies like to do this. Something has to be bounded so it not just knocks that term out. We will have a couple of times in class where we set something equal to 0 to remove a boundedness condition, but not very often. We have a couple of times where we'll do that. But I'm always fascinated how, chemies just say, well, this is infinity, so you got to get rid of it. And by the way, we will we will do some of this when we start talking about the special functions. So now we go back to Newton's law for viscosity. We substitute our result from the previous page here. This is equation 16 into Newton's law for viscosity, and we now have a relationship with velocity, and we have a derivative in terms of radius, and then we still have our pressure gradient term. We have our viscosity term here and our radius term there. We again perform an indefinite integration. Of course, we separate and integrate, so we move the dr over to the other side. So again, we have the integral of r dr, which again is r squared over 2. And again, we have the velocity profile at r is equal to big R, and big R is the center. Big R is the wall, my apologies. You have no slip at the wall, so that has to be 0. R equals 0 is the center, my apologies. And so this C coefficient is not 0. You have to set this equal to 0, so C is equal to the positive side of this. So you get the pressure gradient divided by 2 mu, and then you have big R squared over 2. And when you substitute these together, you get a velocity profile that is a function of radius squared. And I'm again just writing this out in this fashion so you can see that the velocity profile in this case is again the pressure gradient term multiplied by big R squared, which is the distance to the wall, and then 1 minus R squared, which is the center line, or the distance measured from the center line, and then big R squared, which is the distance to the wall. Why did we do it this way? Because it's obvious that at the center line you have the maximum velocity. Okay, so if you set little r equal to 0, that velocity is a maximum. So from now on, what you'll think of is anytime you're dealing with a laminar flow system, where is the maximum velocity? In the center line. Okay, and that's exactly what the graphic on the other side shows. They made this graphic be vertical, but it would be the same as if it were horizontal. So you're looking at a parabolic velocity distribution like this. And again, the point of interest that we're talking about right now is there, and it's defined by this. Okay. I mentioned here, and I'm just going to say anything in blue you can kind of ignore for the moment, but what Bird, Stewart, and Lightfoot tried to do was they tried to say, okay, there is a term where we multiply beta, which is a slip coefficient or a coefficient of sliding friction, and they multiply that by velocity. And then what I did is I reworked all the calculus through with that beta term. And what they're really saying is, and I want to use this very carefully, this is not non-Darcy flow. This is just their simple book problem concept for what? For slip at the wall. This is not non-Darcy flow. This is not non-laminar flow. This is just a simple condition of slip at the wall. What's that going to do? It's probably just going to manifest itself as a shift in the parameter. This is a book problem. This is not a thermodynamic or physically consistent approach. This is just a suggestion that you could use a coefficient of sliding friction to represent behavior at the wall. Okay, and again, I'll ignore it for the sake of argument. What we're going to do now is show the summary of results so far that's here. And if you perform this derivation with the slip coefficient, this is what you get. And you can see that the slip coefficient does show up as a shift, because if you're looking at r equals 0, then the slip coefficient is sort of a shift to that. Now what we need to do is we need to calculate the volumetric average flow rate. So we integrate over r and over theta. So we're doing a double integral. The velocity profile is in r and theta. So we then integrate that, and then we divide by the cross-sectional area, which of course is again an integral of r and theta, but of course it's just going to be pi r squared. So I simplified these forms up here, the velocity form, to be a bit more compact. So this coefficient and this coefficient, A and B, it's just to do the math easier. And so then we substitute those into the area calculation. Of course, we get pi r squared, big R, and then we substitute it into the to the flow rate equation. We substitute the velocity in the flow rate equation, and we work out all the algebra. We have a big R squared, 2 pi big R squared, then the gradient term, then a 4 now instead of a 2, and a mu, and an r squared over 4. Again, multiplying through everything, we have the 2 canceling with the 4, which leaves an extra 2. That multiplies by that 4, which gives us 8. We have a pi here, so we end up with pi r to the 4th, 1 over mu, difference in pressure, or the gradient, P0 minus PL over L. And what does that look like, class? That's exactly Pazouillet's equation that we derived before. So not a lot of bells and whistles here, straightforward. We're at 8:30, we're done, right? Wrong. We got to cover a little bit more. Okay. So now we skip out of this, and we just summarize. Here's all our relationships. Hope everybody's happy. They're all beautiful. And then we talk about, what does this actually look like? Well, if we look at this relationship and we look at a piece of pipe, what's the pressure profile in it going to look like? It's steady state, so what's the pressure profile going to look like? Anybody? It'll be a straight line. Okay. Now, if we plot, and you'll see me doing this a lot, the velocity, which is the flow rate divided by the cross-sectional area, and then what's left over, this P0 minus PL over mu L, what's that give us? Well, that gives us that the pressure gradient is proportional to velocity. That's laminar flow. But then when it rolls over, it's proportional to velocity squared. So you can see that this would define this laminar flow region as a straight line, which is exactly dictated by this equation. But if we see performance start to deviate like this, what does that tell us? It tells us that we have non-laminar flow. Can you remember where we saw this before? What's this, a quick and dirty, sort of tricky hand-waving definition? This is Forkheimer's equation. Okay. All right. Okay, so the last thing we'll do is talk a little bit about what the generalized forms look like. And when we take a look, starting with equation 42, we need to know how we want to define things. This system is in the CGS system. It's centimeter, grams, seconds. So the volumetric flow rate is centimeters cubed per second. The cross-sectional area is centimeters squared. The pressure change is atmospheres, and viscosity is in centipoise. 1 centipoise equals 1/100th of a gram per centimeter per second, or 1/100th of a poise. And then the differential distance is in centimeters. I have no idea why they used all of this, but they did. So if we want to define a quote-unquote Darcy, we have to assume that what we're looking at is a system, and again, we come back to 41. So we're solving for the units of K, okay? And we're going to say the contrived units are going to be a Darcy. 1 centimeters cubed per second, 1 centipoise defined as 0.01 grams per centimeter per second, and then 1 centimeter squared, acting over 1 centimeter distance and acting over 1 atmosphere pressure drop. 1 atmosphere is actually defined as 1.01325 times 10 to the 6 dynes per centimeter squared. And then, of course, everybody remembers what a dyne is. I wouldn't have any idea. It's a gram centimeter per second squared. So 1 atmosphere is equal to all this. So we have to convert atmospheres to the CGS system as well. So substituting everything into this, 1 Darcy would be defined as 9.86923 times 10 to the minus 9 centimeters squared. Well, how big is that? All right. So let's take the average human hair, which is 1/1000th of a centimeter, and what we'll do is we'll assume we're not talking about the permeability of a hair. We're talking about the permeability of a tube the size of a hair. Okay. So what's the conductance of that? So we take and convert that to an area, and then we divide by the coefficient, and the permeability of an equivalent tube that would be the diameter of a human hair is what? 80 Darcys. When's the last time you guys thought about that? So I don't want to sacrifice one, but ow. So if we take that thing and treat it like a single tube and calculate the permeability, it's 80 Darcys. Okay. Cam, where's an 80 Darcy reservoir? There are none. We'd have to have a sand pack with pretty coarse sand, in fact, really coarse sand, to get to 80 Darcys. So the equivalent diameter or the equivalent radii defined by 1 human hair is more fluid, has more fluid conductance capacity than any rock in the world. That's pretty scary. Okay. That's pretty scary. All right, the last thing we're going to do is some field unit conversions. It won't be too painful. Okay, so the first thing we're going to do is we're going to recognize that our dimension system is atmosphere, cc's per second, centipoise, centimeters, Darcys, centimeters squared. So how does it work, class? The units we want, PSIA, reservoir barrels per day. I know you could say it's stock tank, but we'll just go with reservoir. Centipoise, thank God for that. Feet, whatever the hell that is. Millidarcys, that's 1,000th of a Darcy. Feet squared, whatever the hell that is. So we convert from the desired units to the Darcy units. So we start by multiplying PSI. There's how many PSI are there in 1 atmosphere? 14.696. We look at the rate in reservoir barrels per day. There's 5.615 cubic feet per barrel. There's 12 inches per foot. Cube that to get rid of that. Then there's 2.54 centimeters per inch. Cube that. We have 1 day is 24 hours. 1 hour is 3,600 seconds. Well, that makes sense. So somehow that's going to all work out to be reservoir barrels per day. Viscosity is viscosity. Thank God for that. We have 12 inches per foot multiplied by 2.54 centimeters per inch. Then we look at permeability. We have 1 Darcy, and we're actually looking at 1,000 millidarcys. That's the same units. So then we 1,000 millidarcys is equal to 1 Darcy. Pardon me. Area in feet squared, 12 inches per foot squared, 2.54 centimeters per inch squared. Working out all of the units are there. Working out the coefficient is 887.289 multiplied by the remainder of the equation. Delta P is equal to 1 over 1.27 times 10 to the minus 3. And then that's, again, our Q, U, delta X, K over A. Does anybody recognize this number, this coefficient? Yeah, you do? What happens if we multiply that number by 2 pi? For the radial system, what do we get? 7.078 or something like that. Yeah. What's 1 over that? 141.2. Okay. So the units all work out. It's okay. I'm not going to go through the metric units because I hate the metric system. No, actually, just it's fairly straightforward. What's a kPa? Kilopascal. Okay, then we have meters cubed per day, and then we have megapascal per second. Wait, we got kilopascals and megapascals. There's an inconsistency, right? But that's the way life is. Then we have meters, millidarcies, meters squared. When you took Dr. Valco's class, how did he handle all this? Did he just work in standard meter-based system, meter, kilogram, etc.? Okay. What should we be doing? What should we work in? It's irrelevant because we got what we got. I don't know if I told you guys this, but I have a little secret. I didn't really put this in my resume, but for about 4.5 years, I worked on a project in Mozambique, and we went from cradle to grave, from start to finish of a degree program in 3 years. And I had some truly phenomenal faculty that I brought to the project, and they did a great job. But very first class, drilling class, the professor starts talking, and the student stands up and he goes, "Halt!" And the professor's like, nobody ever does something like that. Well, it turns out in Mozambique, the students have a union, and they have a union leader who's elected, and they can go on strike. It's a socialist country. It is a socialist democratic country, whatever. And so this gentleman was not the leader, but he was expressing the sentiments of the group. So he said, you guys ready for what he was going to do? He said, we refuse to work in any other system but the metric system. And the drilling instructor, he just kind of went, me too. And they were like, what? They thought they had won. They thought that, we were going to convert everything to metric and everything else. And he goes, find me some metric drill pipe. And they go, what's drill pipe? we knew we had a problem. And he goes, there ain't no metric drill pipe. He's as driller focused as you can be. And then, find me something else. And they're like, we have no idea what you're talking about. He goes, good, then be quiet and let's go on. But yeah. Does anybody have metric drill pipe? In China, do you use metric system for drill pipe? No. Yeah. So 8-round API threads on drill pipe. Yeah. It's a global standard. What happens if you don't use 8-round threads? You got a bunch of drill pipe that can only talk to itself. Tell me about railroads in India. What's the biggest problem with railroads in India? Sorry? They're all different gauges. Yeah. How did that work out? Not so hot. You have to change carriages all over the place. Okay. At any rate, it's your problem now. I'm going to stick with the, what do you call it, the American engineering system. Does it really matter? When I was your age, I used to worry about this, but all the software has tables built into it where you just tell it what unit you want for any particular parameter. Now, some of you are taking Dr. Moridi's class, right? Dr. Moridi's only works in what units? Yeah. Why does he have that luxury? Because he worked at a national lab his whole career. Kilograms per second. Do you guys measure oil in kilograms per second? Do you measure gas in kilograms per second? Now, you like kilograms per second, being a chemical engineer. What about you, Joker? You don't really care. Doesn't matter.
I'll take what I get.
Okay. How come we sell oil and gas in volume, not in mass?
Changes. Mass is different everywhere. Depending on density.
So the quality would be determined by that, but the volume stays the same, the volume of something. It's a really good idea. Have you ever had a $5 bottle of wine? Have you had a $50 bottle of wine?
Once.
Have you had a $500 bottle of wine? Have you had a $5,000 bottle of wine? Never seen one. But if you put all four bottles on the table, they'd all look the same. It's what's inside that counts, right? So we measure by volume because we sell by volume. Maybe 100 years from now, when we've converted everything to hydrogen, we'll sell by mass. You'd like that, wouldn't you? You'd like to fast forward to 100 years from now. Did you guys ever hear the story about the guy who was diagnosed with 1 year to live? And he started going to church every Sunday. And the preacher said, you know, this is obviously the kind of a religious thing, but not meant to be religious. And he said, my, you've been coming a lot. You must be wanting to get closer to God. He said, no, nothing like that. He said, you know, your sermons are so boring, they make an hour seem like a lifetime. So my lectures probably make you feel that way too. All right. So tomorrow night we start on, I don't actually remember if it's capillary pressure or not. I got to think about that. Let me close the